Number 1. Hardy's paradox. It represents one of the most recent and devastating challenges to our understanding of quantum reality. In 1992, physicist Lucian Hardy formulated a thought experiment that would fundamentally question whether the universe operates according to local realism. The idea that objects have definite properties independent of observation, and that nothing can influence anything else instantaneously across vast distances. Hardy's scenario involves particles and their antimatter counterparts. In the quantum world, when a particle meets its antiparticle, they annihilate each other in a burst of energy. This is one of the most fundamental processes in physics. Yet Hardy proposed a situation where a particle and antiparticle could coexist without annihilation, creating what should be an impossible state of affairs. The paradox emerges when we consider quantum superposition. Hardy showed that under certain conditions, a particle and antiparticle could exist in a superposition state where they both meet and don't meet simultaneously. In this quantum limbo, they should annihilate each other and not annihilate each other at the same time. The mathematics works perfectly, but the physical implications are staggering. What makes Hardy's paradox particularly disturbing is that it can only be observed through probability calculations after the fact. The moment you try to directly observe the interaction, you collapse the superposition and destroy the very phenomenon you're trying to study. It's as if reality conspires to hide its most fundamental secrets from direct observation. In 2024, experimental physicists finally managed to create the conditions Hardy described. The results confirmed his theoretical predictions and dealt a crushing blow to local realism. The experiments showed that our universe genuinely operates in ways that violate our most basic intuitions about how reality should work. Objects don't have definite properties until measured, and quantum effects can create instantaneous correlations across any distance. The implications extend far beyond particle physics. Hardy's paradox suggests that the classical world we experience is merely an illusion emerging from a quantum foundation that operates according to principles so bizarre they would be considered magic in any other context. Reality, at its most fundamental level, is not made of definite objects with specific properties, but of probability waves and quantum potentials that only crystallize into definite form when observed. Moving from the quantum realm to an even more fundamental challenge, we encounter the measurement problem, perhaps the most profound paradox in all of physics. The measurement problem strikes at the heart of quantum mechanics by revealing a fundamental gap in our understanding of how the quantum world of probabilities transitions to the classical world of definite outcomes. In quantum mechanics, particles exist in superposition states, meaning they can be in multiple conditions simultaneously until measured. Yet every measurement yields a single, definite result. This creates an impossible situation. According to the Schrödinger equation, quantum systems evolve smoothly and deterministically as waves of probability. These probability waves can spread out, interfere with each other, and exist in complex superposition states. But the moment a measurement occurs, this smooth evolution suddenly and violently collapses into a single outcome. The wave function, which described all possible states, instantly reduces to just one reality. The problem is that quantum mechanics provides no explanation for when, how, or why this collapse occurs. The theory perfectly describes what happens before measurement and what happens after measurement, but it's completely silent about the measurement process itself. It's as if the most important transition in physics, the moment when possibility becomes actuality, is governed by magic rather than scientific law. What constitutes a measurement remains undefined. Does it require a conscious observer? Does the measuring apparatus need to be classical rather than quantum? At what point does the quantum system stop being quantum and start being classical? These questions have no agreed-upon answers, despite decades of intense research by the world's most brilliant physicists. The situation becomes even more disturbing when we consider the implications. If quantum mechanics is correct, then the act of observation fundamentally changes reality. This suggests that objective reality, independent of observation, may not exist at all. Different observers could potentially witness different versions of the same quantum event, making truth relative rather than absolute. Some interpretations of quantum mechanics attempt to resolve this paradox by proposing that all possible measurement outcomes actually occur simultaneously in parallel universes. In this many-worlds interpretation, reality constantly branches into infinite parallel realities, with each possible outcome playing out in its own universe. We experience only one branch, but the others are equally real. Other interpretations suggest that consciousness itself plays a fundamental role in collapsing quantum states. This would mean that mind and matter are intimately connected at the deepest level of reality, with consciousness serving as the bridge between quantum possibility and classical actuality. The measurement problem reveals that after more than a century of quantum mechanics, we still don't understand the most basic process in physics. The lack of consensus among experts is deeply troubling, because it suggests that our most successful physical theory is built on foundations we don't comprehend. Perhaps the most visceral illustration of quantum strangeness comes from Schrödinger's cat, a thought experiment that demonstrates how microscopic quantum weirdness can theoretically scale up to macroscopic absurdities that assault our common sense. Erwin Schrödinger devised this thought experiment in 1935 to highlight the apparent absurdity of quantum superposition when applied to everyday objects. The setup is deceptively simple. A cat is placed in a sealed box along with a radioactive atom that has a 50% chance of decaying within an hour. If the atom decays, it triggers a mechanism that releases poison and kills the cat. If the atom doesn't decay, the cat remains alive. According to quantum mechanics, until the box is opened and observed, the radioactive atom exists in a superposition of decayed and not decayed states simultaneously. This means the triggering mechanism is both activated and not activated. The poison is both released and not released, and consequently, the cat is both dead and alive at the same time. This conclusion violates everything we know about reality from everyday experience. Cats are either alive or dead, never both. Yet quantum mechanics seems to demand that macroscopic objects can exist in these impossible superposition states until observation forces them to choose a definite condition. The paradox becomes truly disturbing when we consider what happens at the moment of observation. When someone opens the box, the superposition supposedly collapses instantly, and the cat becomes either definitively alive or definitively dead. But this raises profound questions about the nature of reality and consciousness. Was the cat actually in superposition before observation, or does quantum mechanics simply reflect our lack of knowledge about the cat's true state? If the cat was genuinely in superposition, what role does consciousness play in collapsing quantum states? Does reality require conscious observers to exist in definite form? Some interpretations suggest that the cat, as a macroscopic object capable of self-observation, would collapse its own quantum state without external observation. This would mean that consciousness, or at least complex information processing, might be necessary to maintain definite reality. Other interpretations propose that quantum decoherence through interaction with the environment eliminates superposition long before any conscious observer opens the box. The most radical interpretation suggests that the cat is simultaneously alive and dead until observed, and our observation doesn't reveal a pre-existing reality, but actually creates that reality through the act of measurement. This would mean that reality is not discovered, but constructed through observation, making consciousness a fundamental component of physical existence, rather than an emergent property of complex matter. The implications of Schrödinger's cat extend far beyond a simple thought experiment. Modern quantum technologies like quantum computers and quantum sensors routinely manipulate particles in superposition states, suggesting that the strange world Schrödinger described isn't just theoretical, but forms the foundation of cutting-edge technology. Yet we still can't explain why quantum superposition seems to disappear at the macroscopic scale, or what determines the boundary between quantum and classical behavior. This brings us to an even more counterintuitive paradox that seems to reverse the normal relationship between observation and change. The quantum Zeno effect demonstrates that the act of frequent measurement can actually freeze a quantum system in place, preventing it from evolving naturally. Named after the ancient Greek philosopher Zeno of Elea, who posed paradoxes about motion and time, the quantum Zeno effect reveals that watching a quantum system too closely can stop it from changing. In classical physics, observation is passive. We can watch a ball roll down a hill without affecting its motion. But in quantum mechanics, observation is an active intervention that fundamentally alters the system being observed. The effect works like this. Imagine a radioactive atom that should decay over time according to quantum mechanical probabilities. If you measure the atom frequently enough, checking whether it has decayed, you can actually prevent the decay from occurring. Each measurement resets the quantum system back to its initial state, effectively freezing it in time. This isn't just theoretical speculation. Physicists have experimentally demonstrated the quantum Zeno effect using trapped ions, atoms, and photons. By measuring quantum systems at rapid intervals, they can suppress natural quantum evolution and keep particles locked in specific quantum states indefinitely. The effect is now used in commercial magnetometers and quantum sensing devices. The philosophical implications are staggering. In Zeno's original paradox, he argued that an arrow in flight must be motionless at any given instant, yet somehow it moves. The quantum version suggests that observation itself creates the paradox by imposing classical definite states onto quantum systems that naturally exist in fluid superposition. The quantum Zeno effect implies that consciousness or measurement apparatus might have godlike power over quantum reality. By choosing when and how often to observe a system, we can control its evolution through time. This makes observers not just passive witnesses, but active participants in determining the flow of physical processes at the quantum level. Recent research has discovered that biological systems might exploit the quantum Zeno effect for navigation and energy transfer. Birds may use quantum measurements in their magnetic sensors to freeze certain quantum states and enhance their ability to detect Earth's magnetic field during migration. Plants might use similar quantum measurement effects to optimize energy transfer in photosynthesis. If biological systems routinely manipulate quantum measurement effects, then consciousness might be fundamentally quantum mechanical rather than classical. Our brains could be quantum measurement devices that constantly collapse superposition states, creating the definite classical reality we experience from the quantum probability soup underlying all existence. This leads us to perhaps the most existentially terrifying paradox in modern physics, the black hole information paradox, which threatens to destroy our understanding of how information and reality itself behave. The black hole information paradox emerges from the collision between quantum mechanics and general relativity, two pillars of modern physics that seem fundamentally incompatible when applied to black holes. The paradox centers on what happens to information when matter falls into a black hole, and then the black hole eventually evaporates through Hawking radiation. In the 1970s, Stephen Hawking discovered that black holes aren't perfectly black, but emit radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to slowly evaporate, eventually disappearing completely. But Hawking's calculations suggested that this radiation carries no information about the matter that originally fell into the black hole. This creates an impossible situation. Quantum mechanics demands that information can never be truly destroyed. The quantum state of every particle contains information about its history and properties. If this information were permanently lost when black holes evaporate, it would violate the fundamental principle of unitarity that underlies all of quantum mechanics. The paradox becomes acute when we consider the page time, calculated by physicist Don Page. This is the point during black hole evaporation when information should start emerging from the black hole if unitarity is to be preserved. But the page time occurs when the black hole is still enormous, nowhere near the microscopic size where exotic quantum gravitational effects might come into play. This means that under conditions comparable to those in everyday environments, the known laws of physics appear to break down completely. Information either vanishes into nothing, violating quantum mechanics, or it escapes from regions where escape should be impossible, according to general relativity. Recent theoretical breakthroughs suggest that information does eventually escape from black holes, but through mechanisms so bizarre they revolutionize our understanding of space and time. The holographic principle proposes that all information about the interior of a black hole is encoded on its two-dimensional surface, like a hologram that contains three-dimensional information. Even more disturbing is the suggestion that space and time themselves are not fundamental, but emerge from more basic quantum information processing. In this view, the geometry of space-time is constructed from quantum entanglement between information bits. Black holes don't destroy information, but rather reveal that space and time are illusions created by quantum information dynamics. This implies that reality as we experience it, with its three dimensions of space and one dimension of time, is merely a projection of some deeper informational reality, operating according to principles we barely understand. The black hole. Information paradox suggests that everything we think we know about the nature of space, time, and matter might be fundamentally wrong. The paradox also raises profound questions about the nature of memory and identity. If information can be scrambled and encoded in ways that make it practically inaccessible, what does this mean for the continuity of consciousness and personal identity? Are we stable beings with continuous existence? Or are we constantly being destroyed and reconstructed from quantum information in ways we cannot detect? These questions become even more unsettling when we consider the possibility that our entire universe might be the interior of a black hole in some higher dimensional space. If so, the information that defines our reality might be encoded on a distant boundary that we can never access or observe directly. Moving beyond the terrifying implications of information paradoxes, we encounter one of the most chilling challenges to our assumptions about life and intelligence in the universe: the Fermi paradox, which forces us to confront the possibility that we are utterly alone in a cosmos that should be teeming with civilizations. The paradox emerges from a simple but devastating calculation. Our galaxy contains hundreds of billions of stars, many with planetary systems that could harbor life. Given the vast age of the universe and the apparent ease with which life arose on Earth, advanced civilizations should have had billions of years to develop interstellar travel and spread throughout the galaxy. By all reasonable estimates, we should be surrounded by evidence of alien intelligence. Yet when physicist Enrico Fermi posed the question during a 1950 conversation at Los Alamos, asking, "Where is everybody?" the silence was deafening. Despite decades of searching with increasingly sophisticated technology, we have found no convincing evidence of extraterrestrial intelligence. No radio signals, no megastructures, no signs of galactic engineering projects that advanced civilizations should have completed eons ago. The mathematical reality is staggering. Even if interstellar travel were limited to a tiny fraction of light speed, a single civilization could colonize the entire galaxy in just a few million years, a blink of an eye in cosmic terms. With billions of years available, thousands of civilizations should have had time to spread across every star system, making their presence unmistakable. This absence of evidence becomes genuinely frightening when we consider the proposed solutions. Perhaps the most chilling is the dark forest hypothesis, which suggests that the universe is filled with predatory civilizations that destroy any species foolish enough to reveal its existence. In this scenario, advanced aliens maintain absolute silence because broadcasting your location is equivalent to painting a target on your civilization. According to this theory, space is like a dark forest where every civilization is a hidden hunter, moving silently and ready to eliminate any threat. The moment you make noise, reveal your position, or attempt to communicate, you invite annihilation from species whose intentions and capabilities you cannot possibly understand. The silence we observe isn't absence, but terror, a cosmic conspiracy of mutually assured destruction. Another equally disturbing possibility is the Great Filter hypothesis, which proposes that there's some evolutionary bottleneck so difficult that virtually no species survives it. The terrifying question is whether this filter lies behind us or ahead of us. If it's behind us, we might be among the first intelligent species to emerge in our galaxy. But if it's ahead of us, it means that every civilization eventually encounters some insurmountable challenge that leads to extinction. The filter could be anything. The development of self-replicating technology that destroys its creators, ecological collapse, nuclear war, artificial intelligence that eliminates its makers, or something we haven't even imagined yet. The fact that we see no evidence of advanced civilizations suggests that whatever this filter is, it's extraordinarily effective at preventing species from achieving long-term survival and expansion. Even more unsettling is the possibility that advanced civilizations transcend physical reality entirely, moving into virtual worlds or alternate dimensions that make them invisible to our primitive detection methods. They might exist all around us, but operate on scales or in realms that our current science cannot access or even conceive. The Fermi paradox ultimately forces us to confront three equally disturbing possibilities. We are alone in a universe that should be filled with life. We are being deliberately ignored or hidden from by superior intelligences, or we are facing the same extinction event that has already claimed countless civilizations before us. From the cosmic scale of potential civilizations, we turn to paradoxes involving mathematical infinities that reveal the fundamental limitations of our physical theories and point toward breakdowns in our understanding of reality itself. Physical infinities appear throughout modern physics, like cracks in the foundation of our theoretical edifice, revealing places where our mathematical descriptions of reality simply break down and produce nonsensical results. These infinities aren't mathematical curiosities, but genuine failures of our most fundamental theories to describe the physical world coherently. The most troubling infinities emerge when we try to describe particles as point-like objects with zero size. An electron, treated as a mathematical point, would have infinite electric field strength at its location, infinite electromagnetic energy, and since energy equals mass according to Einstein, infinite mass. If the electron has spin, an infinitely small spinning object would rotate with infinite velocity and possess infinite rotational energy. These infinities cascade through the equations, making it impossible to calculate even the most basic properties of matter. The electron should have infinite mass, infinite energy, infinite charge density, and infinite rotational speed. Yet electrons clearly exist and have finite, measurable properties. The mathematics that describes them perfectly in most situations produces completely meaningless results when pushed to their logical conclusions. Similar infinities plague our understanding of gravity and space-time. In Einstein's general relativity, massive objects create curvature in space-time, but when matter collapses to infinite density, as in black hole singularities, the curvature becomes infinite as well. At these points, the theory predicts infinite tidal forces, infinite space-time distortion, and the complete breakdown of physical law. The Big Bang singularity represents perhaps the most fundamental infinity problem in physics. According to general relativity, the universe began from a point of infinite density and infinite temperature, where all the laws of physics ceased to make sense. Before this moment, time itself didn't exist, making it meaningless to ask what came before the beginning. These infinities reveal that our current theories are incomplete approximations rather than fundamental descriptions of reality. They work brilliantly within certain limits, but catastrophically fail when extended to extreme conditions. The infinities serve as signposts indicating where new physics must emerge to replace our current understanding. Quantum field theory attempts to resolve some infinities through a process called renormalization, essentially subtracting one infinity from another to produce finite results. While this mathematical trick works remarkably well for making predictions, it feels like sophisticated bookkeeping rather than genuine understanding of what's physically happening. The persistence of infinities in our fundamental theories suggests that reality at its deepest level operates according to principles we haven't discovered yet. Space and time might not be continuous, but discrete at the smallest scales. Matter and energy might have minimum possible values that prevent infinite concentrations. Or perhaps infinity itself plays a fundamental role in the structure of reality in ways we cannot currently comprehend. These mathematical breakdowns point toward the need for a theory of quantum gravity that can handle extreme conditions without producing meaningless infinities. Such a theory would necessarily revolutionize our understanding of space, time, matter, and energy at the most fundamental level. The final paradox in our exploration combines the strangeness of quantum mechanics with the mystery of consciousness and observation, revealing correlations that seem to transcend the speed of light and challenge our basic notions of locality and realism. The EPR paradox, proposed by Einstein, Podolsky, and Rosen in 1935, represents Einstein's most profound challenge to quantum mechanics and his desperate attempt to preserve classical realism in the face of quantum strangeness. The paradox demonstrates that quantum entanglement allows for correlations between distant particles that seem to require instantaneous communication across any distance. When two particles become entangled, measuring one instantly affects the other, regardless of the spatial separation between them. If you measure the spin of one entangled particle and find it pointing up, you immediately know that its partner will be found pointing down, even if it's on the opposite side of the galaxy. The measurement of one particle seems to instantly determine the properties of its distant partner. Einstein found this spooky action at a distance so disturbing that he argued quantum mechanics must be incomplete. There had to be hidden variables, unknown properties that predetermined the measurement outcomes and eliminated the need for instantaneous influence. The particles weren't communicating faster than light. They were simply revealing properties they possessed all along. For decades, this remained a philosophical debate with no experimental resolution. Then in 1964, physicist John Bell proved mathematically that no theory based on local hidden variables could reproduce all the predictions of quantum mechanics. Bell's theorem showed that the correlations observed in quantum entanglement genuinely exceed what any classical theory could explain. Subsequent experiments have repeatedly confirmed Bell's predictions, demonstrating that quantum entanglement produces correlations that violate the fundamental assumptions of classical physics. The universe really does exhibit non-local connections that transcend space and time in ways that Einstein found impossible to accept. Recent extensions of the EPR paradox have created even more disturbing implications for the nature of reality and observation. In the Wigner's friend paradox and its modern variations, multiple observers measuring entangled quantum systems can reach contradictory conclusions about what actually happened during the measurements. These extended paradoxes suggest that the outcomes of quantum measurements might not be objective facts, but rather subjective experiences that differ between observers. Two physicists performing the same experiment on entangled particles could legitimately reach opposite conclusions about the results, with both being correct from their respective perspectives. This leads to the profoundly unsettling possibility that observed events are not absolute, but relative to the observer, similar to how motion is relative in Einstein's relativity. Reality itself might be observer-dependent, with no single objective version of events that all observers would agree upon. The implications extend far beyond physics into the realm of consciousness and the nature of experience itself. If quantum measurements can produce observer-dependent outcomes, then consciousness might play a fundamental role in determining physical reality rather than simply observing it passively. These paradoxes collectively paint a picture of a universe far stranger than anything our classical intuitions could imagine. Reality appears to be fundamentally quantum mechanical, observer-dependent, and riddled with infinities and impossibilities that challenge our deepest assumptions about the nature of existence. What makes these observer-dependent realities truly terrifying is their implication for the stability of existence itself. If different observers can witness fundamentally different versions of the same quantum event, then the shared reality we assume we all inhabit might be nothing more than a comforting illusion. The universe could be fracturing into countless subjective realities with each quantum measurement, creating a multiverse of experiences where truth becomes meaningless. This observer dependence becomes even more disturbing when we consider modern quantum technologies. Quantum computers routinely manipulate entangled particles to perform calculations that would be impossible in classical systems. Every quantum computation potentially creates multiple observer-dependent realities, each containing different computational results. The quantum internet, currently under development, would link quantum computers across the globe through entangled particles, creating a network where information exists in superposition until observed. The philosophical implications are staggering. If quantum mechanics is correct, then every conscious observer might inhabit their own private version of reality, with quantum measurements serving as decision points where realities diverge. We could be living in a universe where objective truth doesn't exist, where every observation creates rather than reveals reality, and where consciousness serves as the fundamental force that shapes the physical world. Recent experiments have pushed these paradoxes to their breaking point. Researchers have created quantum systems where the very concept of measurement becomes undefined, leading to situations where it's impossible to determine whether a measurement has occurred or not. These experiments suggest that the boundary between observer and observed, between consciousness and physical reality, might be far more fluid than we ever imagined. The most unsettling aspect of these consciousness-related quantum paradoxes is what they suggest about death and the continuity of experience. If consciousness plays a fundamental role in collapsing quantum states and creating definite reality, what happens to that reality when the conscious observer ceases to exist? Does the universe continue to exist in definite form, or does it revert to pure quantum possibility until another consciousness emerges to observe it? Some interpretations suggest that consciousness might be immortal in quantum mechanical terms, with each possible death event creating a branch of reality where the observer survives. In this quantum immortality scenario, consciousness would always find itself in the branch of reality where it continues to exist, making death impossible from the perspective of the dying observer. These paradoxes reveal that consciousness might not be an emergent property of complex matter, but rather a fundamental feature of reality itself, as basic as space, time, and energy. The hard problem of consciousness, the mystery of why subjective experience exists at all, might be intimately connected to the measurement problem in quantum mechanics. Perhaps consciousness doesn't arise from matter, but rather matter arises from consciousness through the process of quantum observation. These 10 paradoxes reveal a universe far more alien and terrifying than anything science fiction could imagine. From particles that exist in impossible states to black holes that threaten the very concept of information. From the deafening silence of empty space to infinities that shatter our mathematics, we've glimpsed the fundamental strangeness underlying reality itself. Each paradox represents a crack in the foundation of everything we thought we understood, forcing us to confront the possibility that objective reality might be nothing more than a comforting illusion. the universe doesn't just challenge our understanding. It demolishes our confidence in the nature of existence itself, leaving us with the unsettling realization that we may never truly comprehend the reality we inhabit.